Okay, folks, let's look at the mechanical energy and the non-conservative force, and we're also going to look at in this video I want to show you certain things that are very important for the exam questions when you're answering questions when it comes to work energy theorem, mechanical energy, work done by non-conservative force. Now let's start by saying um, this object, if it goes up, right, let's say it's moving in that direction, right? When it moves in that direction, that object, there will be a force there, which is the FG parallel, and there will be a friction force there. So in a real life situation, there will be there will be those forces. So those forces, guys, it's the conservative and non-conservative force. Let's say if we do the F net of those forces, it's FG parallel plus FK. That's the net force of the forces that are um, 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 that's the net force of the forces that are doing work there. Let's say in a situation we are doing a work, we're taking this object up an incline there, right? Now, if we take that object up an incline, the object will end up there, right? Will end up there with that displacement, the displacement there, right? So the force that is acting there, it's an FG parallel and an FK. It's a conservative and non-conservative force. It's the same way if you take an object here. The main thing is to put the object up there, right? So you take this object and you displace it there. So if you displace it there, your force that is acting on this object is a gravitational force that is going down, right? So, and here the gravitational force, which is Fg parallel, is going down, and your displacement is going there. Your displacement is going up there. So the work done here in this situation, all I can say, the work done, all I can say in this situation is doing a negative work. What I'm saying, guys, the work done by gravity here is doing the negative work, right? Now, another thing that is important here, guys, that you need to note, the work done by gravity, which is the Fg, is the same as the work done by Fg parallel. Remember, the gravitational force is a conservative force. The work done that is done by it is the same everywhere. It doesn't matter which path it took. So the gravity here is the same. The work done by this gravity that is straight down is the same as the work done by this gravity, which is the Fg parallel there. It's very important. Now let's say the work net, here we have an F net and the conservative force and non-conservative force. Now let's derive this and say the work done by the net force is equal to the work done by the conservative force, which is the work done by gravity, plus the work done by the non-conservative force, which is the Fk. Right, let me put it this way now. So I'll say the work done by conservative force, the WC, guys, it's a work done by conservative force, and the friction is the work done by non-conservative force. Now, since we know from work energy theorem, the work net is equal to change in kinetic energy. Now what I'm going to do, the work net, since is equal to the change in kinetic energy, I'm going to replace this work net by the change in kinetic energy there. Right, I hope that makes sense. Right, now there we still have work done by conservative force, work done by non-conservative force. Now guys, since I've mentioned earlier that gravity, it's a work done by non-conservative force, so we can simply say here, let me put it in a black color. We can simply say work done by conservative force is equal to Fg delta x cos theta. That's the work done by gravity, or let me put it this way first. Let me put it this way and say work done by conservative force is equal to work done by force of gravity, right? Now guys, now since we know this object, it will be mg. Since we know this object this way, its displacement is the height. Even though it started from there to there, its displacement is the height. So what we can do, instead of x, we can say delta h, right? And then then the angle there, it will be 180. This gravitational force, guys, it's in opposite direction with the displacement, which is 180. Even here, if you take this object from here to here, its height, starting from the initial height to the final height, its height increases as you move it from here. So we can simply say, and even the gravitational force is in the opposite direction with the displacement, so it's 180. So I can say here 180. We know cos 180 is equal to -1, so we'll have negative mg delta h, right? So the negative mg delta h, so we can say here it's a work done by gravity. So it's the same as the work done by conservative force. So we can simply say here negative mg h final minus h initial, changing the delta h there, right? I hope that makes sense, guys. So we can simply say the work done by conservative force is equal to the work done by gravity, which is equal to negative, we know the mg delta h, we can simply say delta ep there. It's a change in gravitational force, right? So guys, all the time when you want to calculate the work done by gravity on an incline and you're not given this angle there, you can simply replace the work done by gravity by this, and don't forget the negative, it comes from 180 there. Now we can go back to what we started here. Now we had the ek there, the change in ek equal to, so the work done by non-conservative force, I'm going to replace it by this. So I'll say negative delta change in gravitational potential energy plus the work done by non-conservative force. Now from this, I want to make the work done by non-conservative force is a subject of a formula. I'll say work done by non-conservative force is equal to, and take this one to that side, is equal to change in ek plus change in ep, right? This formula, guys, now it's what we call, it's the work energy theorem as well. This is the work energy theorem as well. This is the work energy theorem, just like this one, just like this one. This is the work energy theorem, and this is the work energy theorem. Both of them, the work energy theorem, they work interchangeably. It depends on what you want and what you are given, right? So guys, this is the work done by non-conservative force, and it's the work energy theorem, just like this one. But when you define the work energy theorem, you define it according to this one, not according to this one. But this one, I was just deriving it for you. Where does it come from? The important things here, it's this and this and this, right? Okay, now let's look at a situation where it's a closed system. Let's say we have a closed system, right? Closed system. I know when it's a closed system, guys, the net external forces is equal to 0. What does it mean? No non-conservative forces. What are the non-conservative forces again? It's the friction, it's the tension force, it's the force applied, it's the force of an engine, it's the what? It's the air resistance. It's the air resistance. Those are non-conservative forces. So if the system is closed, there are none of these forces. There are none of these forces, right? So that means whatever calculation that you are asked, you can use, you qualify to use the conservation of mechanical energy. You can use the conservation of mechanical energy only if the system is closed. And when they say use the energy principle, when they say use energy principle, you can use the conservation of mechanical energy. You can use the work energy theorem, right? You can use the work energy theorem, this one, and you can use the work done by non-conservative force. The work done by non-conservative force. But here, using the work done by non-conservative force, you must know if the system is closed, that means the work done by non-conservative force is zero. There are no non-conservative forces, so the work done by non-conservative force is zero. So here you have to substitute zero and have that, right? It's very important, very important, that. And let's say now in this case, the system is open system. What do we mean by open system? We mean the work done by non-conservative force is not equal to zero. That means that the net external forces is not equal to zero. That means the non-conservative forces, conservative forces are present. Which one are the non-conservative force? I've mentioned it's the friction. It's the tension, force applied, force of an engine, air resistance, and so forth and so forth. They are present. That means the system is open. Now, if the system is open, they said use the energy principle to calculate whatever, the final velocity to calculate whatever they want to calculate. They demand you to use the energy principle. You cannot use the conservation of mechanical energy. You cannot. The mechanical energy is not conserved. So you cannot use this, guys. It's very important. You cannot use this one, right? The way you can use the formula that you can use the work energy theorems, both of them, this one and this one. You can use these work energy theorems, right? And when the system is open, you must remember that the work done by non-conservative force is not equal to zero. You're not going to substitute zero there, right? And lastly, guys, do not forget that the work done by gravitational force, and which is the work done by gravitational force parallel, is equal to delta HP, which is equal to the gravitation, to the negative change in gravitational force. It's very important, guys, if you're not given the angle.